Okay. Now I am almost ready. Okay. I should say that the homework problem 5 you didn't do very well. Nothing compared to what you have done previously. So please do a better effort with homework 6. Okay. So let's start today's agenda, and it's about integration once more. And this is the last lecture on just integration. But now it is over a solid field and I'm going to start with an intro with a pentahedron. And then I'm going to discuss what is the integration about. And this will be purpose, method, and technique. And then I'm going to discuss again, and the emphasis today is on, again, on parametric representation, because this seems to be the difficult part. So I'm going to talk about solid bounded by a graph surface. I should say here that we use a capital omega to denote a solid field. And then a solid field, so when omega is a solid of revolution. And then finally, I give a short intro to spheres. This is a bit special, how you actually do the parametrization of a sphere. Let me see if I can. Yeah, we have a box over here. This one. Say, if I cut this box here along a diagonal here and along say along a diagonal, well, let me see if I can do it right. Along a diagonal here, and then along a diagonal here, and then I take away the top part. So it's cut along a diagonal here and a diagonal here. And when I take away this, then there will be a pentahedron. A pentahedron is a surface bounded by 5 straight surfaces, plane surfaces. So my question to you is then, what is the volume of what is left? I cut it here, I cut it here, I take this away. So what is the volume of what is left? Did you have any suggestions for that? Yeah? No? Make a guess then. Yeah. 1/4. So the suggestion is 1/4. So any other suggestions? Yeah. 1/6. Okay, should we calculate it? So let me draw it. So I have the usual x, y, z coordinate system, and then I place my box from, say, this is the width of the box, and this is the length of the box. This is square, but let's assume that in general it's rectangular. And then this is the height of the box. So this is the box. So I cut along this diagonal here, and then I cut along this diagonal here. And then I have, say, this is still, and then I remove everything from top. So I am left with this pentahedron. And the pentahedron, you have a triangular surface here, triangular surface here, and then you also have this one here, so you have a triangular surface here and here, and then you have a quadrilateral, a rectangle at the bottom. So what I need to do then is to make a parametric representation for this pentahedron here. And let me start by having a point in the xy plane. And if I take this coordinate and let this be u and this be v, then this point here is u, comma v, comma 0. And I call it q. Now, when you have a situation like this, a good idea is to make the parametrization from this corner here. I call this P, and it has the coordinates 0, 0, c, this point here. And then I draw, I better take another color. Then I draw this vector here. So you see, if I could parameterize this vector here, then I can in fact reach every point in this theta-hedron, because u I can vary between 0 and a, v I can vary between 0 and b, and in that way I can reach any point at the base of this tetrahedron. And then I can use another parameter in order to say where am I on this vector here. So what I want to do is I want to take the point P, and then I want to add a third parameter that indicates where am I on this vector here. What I need then is the coordinates of this vector. So I take the coordinates of the last point, that is u, v, 0, u, v, 0, and then I subtract the coordinates of the initial point, and that is 0, 0, C. And now I'm ready to write down my parameter representation. I have this initial point, which is u, v, 0, that is the point P, and then plus, and then I can subtract these two. I get u, v, and minus c. And I can write it as u times w, that is, sorry, I did it wrong. This is the initial point, and I wrote down the point Q here, so it should be 0, 0, C. That is the coordinates of my key point. So what I get for the first coordinate, I get W times U, the second coordinate W times C, and then finally I get C minus C times W. This is the parameter, or the parametric representation, but I'm not finished yet. I have to write down what are the values of the parameters. You see, U is varying between, well, let me write it as U belongs to the interval from 0 to A. V belongs to the interval from 0 to B. And then finally, W belongs to the interval from 0 to 1. Because whenever W is 0, you are at P, at the point P, and when it is equal to 1, you are at the point Q, and you can reach any point in between. So this is a parametric representation. I have a Maple email showing this, and I will upload it afterwards so you can see it. Now what we want to do now is that we want to then calculate the volume of this tetrahedron. And in order to do so, we need to find out a formula for space intervals. And I'm just going to cite this now. Space intervals, and we are given a function, or given f of x comma y comma z, and a solid omega. And omega has with the parametric representation and this is simply given by 3 coordinates. It's x of u, and y, u, and then finally set u, u. And also, we know that these parameters, they belong to these intervals. So, in parameter space, you have a box, rectangular box, or a box. Then you have these 3 coordinate functions. And if you have this, then you can define the space integral in this way. This is the triple integral, that is f, that is c to d, and then it's a to b of f restricted to the parametric representation of your solid, like this. And then, of course, you have the Jacobi-function. And for space integrals, it looks like this. It's a numerical value of this determinant of this matrix, where in the first column you have, say, the derivative of your parametric representation with respect to the first coordinate, or the first parameter, and then the second parameter as the second column, and then this as the third column. So this is the determinant, and we have the numerical value, and then you integrate with respect to u, v, and w. And this is often called the mass. If F is a mass distribution. Now, if you are only interested in the volume, then you have denoted vol of your solid. Then you just take this space integral of a 1, that is, you put f equal to 1, and then you integrate. And that is, if you use the formula, you're just integrating the Jacobi function. Finally, you have the center of gravity. I have also called it this, the mass midpoint, but if it is a density function you have, then it would be the center of gravity that you're finding. And this will, now we denoted a vector, C, and it has 3 coordinates, C1, C2, and C3, and it is equal to 1 divided by the mass. And then the integral over your solid, and then I'll tell you what this means. I write here x, y, and z, and f x, y, z. And this means that for the first coordinate of the center of gravity, you use x in this evaluation. This is 3 integrals, 1 for x, 1 for y, and 1 for z. The 1 for x gives you the first coordinate, the 1 for y gives you the second, and the 1 for z gives you the third coordinate. Now let's see if we can compute the volume of our tetrahedron. Over here. So what I need to compute the Jacobi function. So I need to find the determinant where the first column here is the derivative of my parametric representation with respect to the first parameter. So I differentiate with respect to u, and I get a w here. The second and third coordinate doesn't depend on u, so I get 0 here and here. Then I differentiate with respect to just correct this. It will be W times V at this point. So when I differentiate with respect to V, I get 0, I get W here, and then I get 0. And finally, when I differentiate with respect to W, I get U, V, and then I get minus C. So this is this matrix, and I have to find the determinant. But it's an upper triangular matrix. So you know that the determinant is equal to the product of the elements in the diagonal. So this will be W squared times minus C. And you have to take the absolute value of this in order to get the Jacobi function. Since C is positive, it's the side of a box. It means that the Jacobi is equal to C squared. So I can calculate the volume. It will be the integral, or the triple integral of 1, and then I should multiply by the Jacobian. And then I integrate u from 0 to a. I integrate v from 0 to b. And then finally, I integrate W from 0 to 1. Like that. C is a constant. I can take it out of the integration, so I get C, and then I get, and then like this. And the innermost integral is then an integration of 1. That is, you need to find an indefinite integral of 1, and that is u. So that will be u taken between the limits 0 and a, and you have to integrate this. Now, when you put in the limits, you get an a from the upper limit, and then from the lower limit, you get 0. So this is a, and I can put this outside the integration. It's a constant. A times c now, and then the integral from 0 to 1. I'm missing something. I hear some murmur, but you didn't correct me. But I should remember this. So you have this with respect to the integration to v. This is a constant you can put outside, and then you get v as the indefinite integral of the one I have left, and then from 0 to b, and then I still have to integrate it up to. Again, when I put in this, I get b minus a 0, so I get a, b, c. That is the constants, and then I have the integral of w squared integrated with respect to w, and an indefinite integral is w cubed divided by 3, and you have to take it between these limits. So finally, you end up with the upper limit gives you 1/3, so you get a, b, c, third. So, and you know, a times b times c is the volume of the whole box. A times b times c. So it's not 1/4 and it's not 1/6, but it's 1/3 volume. What I'm going to do now is that I'm going to try to indicate to you why is the Jacobi function, why does it look like this? And I draw here the axis parallel box, axis parallel box in parameter space. I have u, v, w, and then I have some kind of box, say this. So this is my, this is in fact my solid in parameter space. And then what I can do is that, like we did for the curvilinear case, and we did it for surfaces. We subdivide the box in smaller boxes. So I subdivided each of the directions or partition in intervals, in equidistant intervals. So I get a lot of small boxes, and then I approximate, say, the total integral of my density distribution or my mass distribution. Because if you take a point inside, you can approximate the value of the mass function in that small box by the value of the mass density in the lower left corner. And then if you multiply by, say, by the volume of that, you get an approximation of the mass of that small part. And if you then sum all these small parts of the whole box, then you get an estimate of the total mass. So I just write down that I have partitioned this, and I have an index y, an index j, and an index k. And then I take the value ui, uj, and ui, vj, and wk. And this is in all these points that I have divided this into. And then I multiply by the length of the interval in the u direction, the length of the interval in the v direction, and the length of the interval in the w. And this is in fact the volume of this small box here, and multiplied by this, it's an approximation of the mass. And then I sum it all. And the good news is that if you go to the limit, you get this integral here, the integral from E to F, C to B, and A to B of your mass density, du dv. So this is the limit as the number of subdivision goes towards infinity in each of these directions. You get this one. And again, you can start by computing the innermost integral, and then the next one, and then the last one. This is the case when it is axis parallel. But what if it is not axis parallel? Then you need the Jacobi-function. So, I write here not axis parallel. But you still can go this. You still have your parameter box. U, C, and W. So I have, say, this box here. So this is the box in parameter space, and it is axis parallel. But through this parametric representation, this is mapped onto the x, y, z plane, and it may look something like this. Some peculiar shaped solid in free space. But what if I took one of the small boxes here, say, I take this one here, and this may be mapped through this parametric representation R here. It may be mapped into something looking like this. You have, say, if this is the upper part, and this down here is the lower part. It will be deformed in a sense. This point here will be mapped into this point here. And what we want to do, or what we want to calculate, is then what is the volume or the approximate volume, and then the mass, because we multiply by the mass density of this volume here. And here we use the tangent vectors. This one here will be in the R prime U. This one here will be R prime V, and the last one here will be R prime W. So you have these three tangent vectors, and when you then multiply by the length of these, then you get approximate values, first order approximate values of the lengths of each of these sides in the deformed So in fact, what you are doing is that you are taking this something. So you take this parallelepipedon here, and then you approximate the volume of this by the product of these sides here. And then if you multiply by the mass density in this corner point, you get an approximation of the mass of this small. So what you end up with, that you have the Jacobi. This is the function of u minus w. And then this will be because you're mapping this into this, and so and you say that this will be the Jacobi function times the volume of the original box here, and then this will be equal to the approximate volume over here. So you get that this will be the determinant of R U delta U, and in the first volume R D times delta D, and then R W times delta to W. And then you see, this is a constant times the volume. You can take this outside the integration. So this will be equal to dv, and also for the second volume and the third volume. And what you end up is with, in fact, you should have the numerical value in order to get this volume, but then you have, and then V, and then finally W. And then you see you can divide through by this, and you end up with the Jacobi function. Just write it down. The Jacobi is equal to this determinant and then finally, and then the numerical value of this. Okay, a break. We resume 5 minutes past 11.
I have a question.
Yeah.
Now you just told us about this Jacobi-function with the determinant of three bases. Yeah. In keynotes, they had another Jacobi-function, I don't know if that's for later, where they have the cross product of the two first, and then they dot the third one on top. Okay, so they're the same. It's not another one that's going to come later.
It's the same one.
Okay, so
In fact, I think there's an exercise showing that it's just in order to get the idea of volume, because this is a normal volume. You take the cross product, and then this is the area of the base, take the height, which is
it's just like, it's a normal volume.
it's a normal volume, but this volume computation is equal to
One question on one earlier lecture.